Hi, and welcome to this lecture on inference. Now, inference is the process of coming to a conclusion or making a decision based on evidence and some reasoning. And in this first of two lectures where we deal with inference, we're going to specifically look at categorical data. In the follow-up lecture, we will look at numerical data. So we will revisit hypothesis testing as well as confidence intervals specifically for categorical data. And we will illustrate the main requirements for inference using R. The case study, if you followed these lectures, is going to be fairly well known, where we're sitting with a machine, a drilling machine, where we drill holes into a piece of material, and these holes have to be within 9.5 to 10.5 centimeters. But this drilling machine is not quite performing as well. So what do we do in our investigation? We take 30 samples. And that means we take 30 pieces of material, we drill a hole in each, and we measure the diameter of the hole. Now, the drilling machine and its output can be seen as a random process. It's not always exactly the same. And we are interested in the true proportion of holes that are according to specification. We want to say something about this drilling machine. Is it performing well or not? But we can never exactly know the true proportion. And therefore, we take samples and we work with the sample proportion. And that's what these 30 pieces of material with the holes in them are for. And the whole idea behind inference is to use the sample proportion to say something about the larger, more vague, nebulous, true proportion. So with inference, we can calculate a confidence interval for the true proportion of defective products. And then we can also conduct hypothesis tests and determine if one machine is really better than another one. Even though we don't know the true proportion, we can base our decision, our inference, our conclusion on the samples. And confidence intervals are particularly handy since it gives us bounds which we can then use, for example, for planning. So if I know what my confidence interval is, I know I have a lower limit, I know that the true proportion is somewhere between A and B. And now I can take a worst case scenario and a best case scenario and plan for both of them and see what the impact actually is. And this is especially useful if we want to produce, say, 1 million products. We want to be quite sure that currently we make the right decision on whether to replace the machine or keep it. But the confidence interval can also be challenged. If you find that these limits, A and B, are too wide, you can calculate, okay, but how many samples do I need to take in order to get a more narrow confidence interval? So the basic process of inference is that we want to analyze the properties of a random process, but we only have a sample to work from. So we take the measurement on the sample, and that gives us a sample parameter, and it can be any measurement. In our case, for this case study, it's going to be the proportion of holes or parts that are within specification. And then we use the sample parameter to infer something about the population parameter, the proportion of parts that are within specification for the entire history and the future of this machine. So the typical tools of inference are confidence intervals and hypothesis tests. And here we specifically work with categorical data. So for both the confidence interval and the hypothesis test, we can calculate the standard error, which is the variance that we actually expect if we have identical experiments. And identical experiments would be like our 30 samples that we're taking. Now, there are formulas to calculate the standard error, and you've done this in engineering statistics. But to use them, you first have to check two conditions specifically. The first one is independence. And with that we mean the samples that you've taken, are they independent from one another? So if we just have 30 pieces of material and we drill a hole in each, we can claim that they are independent from one another. But for example, in something like temperature, it becomes a lot harder to actually prove independence or to show that measurements are actually independent. Because if I take the temperature at 7 o'clock and I take the temperature at 8 o'clock on the same morning, those two measurements are not necessarily independent from one another. Because if I'm interested in the morning temperature, if it is a particularly cold morning at 7, it is likely to still be a little bit chilly by 8 o'clock. So the 8 o'clock measurement will be dependent on the earlier measurement. The second condition that you actually need to check for is when you work with categorical data is that you have at least 10 observed or expected successes and failures. So in our case, parts that are within spec and parts that are out of spec. If you don't have 10, you should be very careful of actually calculating hypothesis tests or confidence intervals. So for the confidence intervals, if the conditions hold that we've just talked about, we can use the standard error and some critical value Z star, which is linked with how confident we want to be with this interval. And we can add it and subtract this from our observed proportion so that we can actually get an interval. And we denote with p hat the sample proportion. So our confidence interval for the true proportion will be our sample proportion, p hat, plus or minus this critical Z value of ours, which relates to a Z value that is associated with, I want to be 90% sure, for example, or I only want to be 50% sure. So we take that critical Z value and we multiply it by the root of the fraction of sample proportion multiplied by 1 minus the sample proportion divided by the number of observations in our sample. So let's demonstrate that quickly in R, and we're going to use the current machine's proportions as we've distributed the data in an earlier lecture. So in R, I created a new project, and I'm now just going to create a new script file, which I'm going to call class example. I like starting with a clean workspace and just read in or load the libraries that I'm going to use. The current machine holes is already available. We've shared it with you in a previous week's lecture, and you can just navigate to that particular file. Mine again is one level up in a data folder called current machine holes. If I recall correctly, the column types, the first one is an integer because it's the sample number, and the second one is a numeric value, which is the hole diameter. And when I read this in, your values might look slightly different than mine. You'll see, yes, indeed, I've got the sample number in the first column, and the second variable is the hole diameter in centimeters. Now, I'm actually interested to know whether these are within or out of spec. I'm not interested in the numerical data, I'm interested in the categories. So I'm going to add a new variable that is called inspec. And here I'm going to assign a binary variable or a Boolean, and I'm going to just evaluate it by checking whether current hole diameter is greater than or equal to 9.5, and at the same time current hole diameter is less than or equal to 10.5. If I look at my data set, you will see that all of the holes that are within specification now have the value true, and those that are out of spec have a value false. Another way to look at it, this is just to look at the call the table function that will aggregate the data for me. It will look at all the possible values and count them for me. I will also need to know n, which is the number of observations in my sample, which is just the number of rows in my data set. And I don't hard code this, I rather calculate it from my data set, because if I later want to load a larger data set, I can do that and I don't have to change my code again. So now that we're ready, we can calculate the confidence interval. Right, so the current proportion is, and here I'm going to work with the proportion of those units that are out of spec. So it will be the 19 divided by n, but I again don't want to hard code this. So instead I'm going to say sum all of the values of the negated variable in spec and divide that by n. So what does this do? The exclamation mark takes the negation, so current in spec is true for those that are within spec. I want it to be true for those that are out of spec, so I negated. Everything that is true becomes false, everything that's false becomes true, and that allows me to simply sum over all of them. And if I execute just that portion, I select it, I can run it, and I see that that indeed is 19, which is the same as the number of units that are false. And if I execute this entire line, I can see that my current proportion of out of spec units is 63.3%. So I can also calculate my standard error for the sample, which is the square root of B current multiplied by 1 minus B current divided by n. And I've got my standard error. Now at this point I need to specify some level of confidence. So let's say I want to be 0.95, 95% sure. Now at this level we need to calculate or look up the specific Z value. Now if you have a statistics table for a normal distribution handy, you can look it up. I'm just going to show you how to calculate this inside R. So I'm just going to call this Z star. And the way in which I do that is to use the quantile function that is available inside R. And it's called qnorm. And if you're not 100% sure how it works, you can just call question mark qnorm and it'll tell you about the normal distribution. So we've got the density, the distribution, the quantile function, and we can generate random numbers. Why do we use the normal distribution? Because from the central limit theorem, we assume that if we want to estimate a true proportion, that our estimate will typically follow the normal distribution. So Z star, the quantile function allows us to calculate the area or in a standard normal distribution, which is what the default is, a standardized normal distribution. We can provide it the p-value and it'll give us the quantile so we're going to call the qnorm function at a specific p. Now the probability at which we want to calculate this, we want to be 95% sure, and if this is a normal distribution, 2.5% will be at the lower tail and 2.5% will be at the upper tail. Now to do that, we're going to do the way in which we calculate that 2.5% is simply by saying 1 minus whatever this confidence level of ours is, which is 0.95, 1 minus that value divided by 2. So that will be our probability, 0.25, and our Z star value in this particular case is minus 1.9599. So we're roughly about 2 standard deviations away from the mean. Now, because we want to manually do this, I'm just going to take the absolute value because it will be one, the one confidence level will be below and the upper limits will be at the top. So I'm just taking the absolute value here. And that allows me to calculate the lower value, which is B current minus the Z star value multiplied by the current standard error. And Ci upper will be plus Z and then I just want to report the values. So I've calculated my Z, calculate my lower, my upper, and I can report the two of them. So I am 95% sure that the true proportion of units out of spec for this current machine, I'm 95% sure that it'll be somewhere between 46 and let's say nearly 81%. If I want to be more sure, I change the confidence level to 99%. I would expect the more certain I am, the wider the confidence level will actually get. Now let's see whether that is indeed true. And there we see it. Now suddenly, instead of 95% sure that the true proportion will be somewhere between 46.1 and 80.6%, if I want to become more sure, I have to widen my confidence interval. Whereas if I'm only 80% sure, I can actually make the confidence interval a little bit more narrow. So the narrower I make it, the less certain I become about my estimate. When we recap hypothesis testing, it's always convenient to use an analogy of a court trial. You've heard the expression, innocent until proven guilty. So the null hypothesis in this case would be that the defendant is innocent, and the alternative hypothesis is that the defendant is actually guilty. And then we present the evidence. In our case, statistically, we collect the data as our evidence, the measurements or the observations that we actually go out and gather. And then we judge the evidence, and we judge it by trying to answer the question, could the data, the evidence that we have, plausibly have happened by chance if the null hypothesis was actually true? And if it is very unlikely to have occurred, if it's very unlikely that we could have seen this evidence if indeed the null hypothesis was true, then the evidence raises more than a reasonable doubt in our minds about the null hypothesis. If the evidence is not strong enough to reject the assumption of innocence, the jury will typically return a verdict of not guilty. The jury does not say that the defendant is innocent, just that there is not enough evidence to convict. The defendant may indeed really be innocent, but the jury just has no way of being sure. So said more statistically, we fail to reject the null hypothesis. We never declare a null hypothesis to be true because we simply do not know whether it is true or not. Therefore, we will never say that we accept the null hypothesis, only that we fail to reject it. So in a trial, the burden of proof is on the prosecution. In a hypothesis test, the burden of proof is on the unusual claim. So the null hypothesis is the ordinary state of affairs, or what we call the status quo. So it's the alternative hypothesis that we consider as the unusual one, and for which we actually will gather the evidence. So how do we go about doing this? We start with stating and expressing our null hypothesis, which represents the status quo. And then we also have an alternative hypothesis that represents our research question, what we're actually trying to test for. So we conduct the hypothesis test under the assumption that the null hypothesis is indeed true. If the test results suggest that the data do not provide convincing evidence for the alternative hypothesis, then we just stick with the null hypothesis. We don't accept it, we simply stick with it because we cannot reject it. If the test results, however, do provide convincing evidence, then we reject the null hypothesis in favor of the alternative. So for our drilling example, we will calculate how many standard errors our observed proportion from our experiment, our 30 samples, how many standard errors away that is from the assumed proportion, which is expressed or denoted by PA under the null hypothesis. So we calculate the standard error as this assumed proportion multiplied by 1 minus the assumed proportion divided by the number of samples. Take the root of that. That gives you your standard error. And then we can actually calculate a Z value, which is our observed proportion, our sample proportion, minus the assumed proportion PA divided by the standard error that we've actually calculated. And associated with the Z value, which we can look up the probability for, we now have an answer to the question, but what is the probability that we would have observed these evidence values if the null hypothesis was indeed true? If we get around to it later, we will also look at how can one simulate the null hypothesis. But let's look at how you do this in R. Right, so we can carry on to calculate and perform our hypothesis test. Now, in this particular case, I'm interested in the number of, or the proportion of successes. So again, I'm going to use the sum function, but now I'm not going to negate the inspec values. I'm simply going to calculate the proportion of successes, divide by n, which is my total number of samples. And if I execute this, you'll see that I get a value, where is it, 36.67%, which is 1 minus the probability or the proportion of out of spec units. Now, let's assume somebody claims that the true proportion of this machine, the proportion of successes is 0.7. That's somebody's claim. So the null hypothesis in this particular case would be to say that, okay, we believe you that this machine is actually performing at a success rate of 70%. So 70% of all units are within specification. That's our null hypothesis. And the burden of responsibility is then to actually prove the alternative hypothesis, to say, but the current machine's proportion is actually not 0.7. So how do we do this particular hypothesis test? We can't just calculate the two and say, oh, they look pretty far apart from one another. That's not good enough. So we want to perform a hypothesis test. So this is now the alternative hypothesis, to say that our current P and this P is not the same. That's the alternative hypothesis, to say that this value PA, which is the claimed proportion of successes, what is the chance that indeed our sample of 30 units come from this distribution with a proportion of 0.7%? It's just random chance that we got a much lower value. What is that probability? Right, so we're going to calculate the standard error, which we've just shown is the square root of the claimed successes multiplied by 1 minus the claimed successes divided by n. That's our standard error that we've actually calculated. and that is 0.837. From here we can actually calculate the z-score, and we do that as taking what we've observed, the real, well, our sample proportion, which is current successes minus the claimed proportion, and divide by our standard error. And that gives us a z-score of minus 3.984. Now, in order to calculate, but what's the probability associated with this value, we actually say, we use the function p-norm, which we've introduced in a previous lecture on the introduction to probability models. And we say, but what is the value in the standardized normal distribution for a Q value, which is this z-score of ours? And to just make it read easier, we're just going to multiply by 100. And the answer here is 0.00338. So the question is, how do you interpret this p-value, this probability value? In a null hypothesis, the null hypothesis stated that this machine, that the true proportion of successful holes is 70%. Now, the alternative hypothesis says, no, this is not true. Our machine does not perform at that particular level. So the question that we're trying to answer here is, what is the likelihood, what is the probability that indeed our current sample comes from this true proportion of 70%? It is just by sheer chance that we actually got a much lower value of, what was it, 36.7%. And the probability of that happening, of us drawing a sample that looks like our current sample, while in fact the null hypothesis is true, which is that our machine really performs at a success rate of 70%, that probability is 0.003386883. So there's a very, very minute chance that that indeed is possible. Now, typically when this p-value is smaller than 10, if there's a less than a 10% chance, that is a sufficient level to actually say, you know what, I think we've proven beyond reasonable doubt that the null hypothesis can be rejected. So that would be our claim here, that the p-value is much, much smaller than 10, and therefore we can reject the null hypothesis.